Alright, so this is active filter design, lecture 38. In the last class, we saw how one might test an active filter, right. While the discussion yesterday was kind of restricted only to, might have given you the impression that it's only valid for GMC filters. It's not true. Whatever box there is inside, right. In fact, it doesn't even have to be a filter. Any two-port network can be tested quite accurately by where you can get rid of the effect of package and all the parasitics that come along with it by using the techniques that I described yesterday. So this with this we have come to the whole process right from approximation to test. So the family of active filters we have seen so far are the GMC filters. Let us quickly recall the problems with these filters and what we might be able to do to fix those problems. What do you think are the problems with these filters? One is limited linearity. Okay. Then one might argue that you have limited linearity, you can always fix things by linearizing the transconductors, but the moment you try to do that, you find that you have excess noise, right, which basically means that the dynamic range is smaller than what it could have been without the excess noise. And please recall that 3 dB excess noise is equivalent to twice the power, right. Okay. Then of course, it is parasitic sensitive. All right, because finally transconductors have to be connected to one another, and you will use wires to connect the output to one transconductor, the input of the other, and these wires will have parasitics to ground, right, which means that these parasitic capacitances will come in parallel with the integrating capacitors, thereby changing the integrating capacitance. So you will find that you either have to account for them, or the parasitics have to be very small, which is equivalent to saying the integrating capacitors have to be very large, which is equivalent to saying that the GM by C is small. So unless if you are working at really high frequencies, you have to be careful about accounting for routing parasitics. Okay. So these are all the problems with GMC filters. What are the good things about these filters? They are very fast. All right. So in practice, these properties basically have limited the use of GMC filters only to those niche applications where very high speed is desired with limited dynamic range. You can see that you cannot get very high speed, and I mean the high speed is coming because of only local feedback or virtually no feedback within the transconductors. For example, if you use a differential pair, it's basically an open loop system as far as the integration is concerned. So that high speed is coming with open loop operation, which will naturally mean that linearity of these systems is not great. The moment you attempt to linearize, you get more noise, so you get stuck with what you have. Okay. So a very successful application of GMC filters is in hard disk drives, right, and the hard disk drive reading channel, or the whole communication channel from the magnetic stuff written on the drive to the final bits that go into your microprocessor is a fantastic communication system, right. Today, I believe the state of the art in how fast you can read data from your hard drive is Yeah, all that is fine. They're stored in a cache and all that stuff. But what do you think is the raw speed at which you can read data from your hard drive? It turns out that the state of the art is probably about perhaps about 2 gigabits per second, right, from the hard drive. I mean, this is like about 10 years back when I was working on these things. It was the state of the art was about 800 megabits per second, right, and the state of the art technology at that time was 0.25 micron CMOS, right. 10 years passed, and the state of the art now is technology wise is people are probably shipping 45 nanometer parts, which means that technology has gone up in speed by a factor of about 10 or so, right. But I would think that the state of the art in data rate of these disk drives is probably in the several, definitely at least 2 gigabits per second. I think probably even higher. So basically, what is happening in a disk drive is the following: you have this platter, right, which has got magnetic material on it, and this platter is a heavy disk. I don't know, those of you who've seen a ripped open hard drive, right? The magnetic disk inside is pretty heavy, right? So it's rotating at a constant angular velocity, and so the read head is flying over the platter, and every time a magnetic domain changes, you basically it induces either a voltage change if you have an inductive type read head, or a resistance change if you have what are called these giant magnetoresistive effect, right, that won the Physics Nobel Prize a few years back. So depending on the kind of read head you have, it will introduce voltage / current changes in the head. These changes obviously, if you want to have more data on the disk, right, what does that mean? You will pack spatially, you will have to pack more bits per unit area. Now if you spatially attempt to pack more bits per unit area, it means that you cannot have magnetic domains which are all the way flipped one way and all the way flipped the opposite way for either a 1 or a 0. I mean, they will only be only staggered very little, and then from that you will have to figure out what the actual bit pattern written on the drive is. Okay. So that's one thing. Another thing is that if the disk is spinning at a constant angular velocity, the data rate at the outer edge of the disk will be much higher than the data rate at the inner end of the disk, right. So not only do you have a channel whose bandwidth is varying, it's also a very high speed channel, right. So at the outer end of the disk, you will probably be reading data at several gigabits per second today. The signal is also very small, so before the DSP can process it, I mean, please note that the signal, it's not a clear 1010 that you can read off directly into your CPU, right. It is a very small signal, probably several tens of millivolts, right, and by visually eyeballing it, you will not be able to make out any data pattern at all, right. So what is done is to use an algorithm which is very common in most communication systems today. This is called maximum likelihood sequence detection, right, and the algorithm used to do it is what is called the Viterbi algorithm. So before you can get to the Viterbi algorithm, you need to basically amplify the signal, right, you need to filter off excess noise, okay, then you need to have an A to D converter which can digitize this received signal, right, to a reasonable resolution. It turns out that in disk drive systems, the SNRs are all of the order of 25-30 dB, right. That is the kind of SNR you require finally at the Viterbi end to decode bits with sufficiently low bit error rate, which means that the analog front end must have, if you need finally 25 dB or 30 dB, then the analog front end must have 1 bit more, right. So must be slightly better, so that the non-idealities in the front end don't impact the bit error rate finally. So, all these systems need only dynamic ranges as far as the analog front end is concerned, a 40 dB dynamic range is all that is needed, right. But the speeds, as you can see, are extremely high. Not only is that a problem, as I indicated to you a few minutes back, the data rate varies by a factor of, typically by a factor of 3 to 1, because at the center of the disk the data rate is much slower because linear velocity is small. At the end of the edge of the outer edge of the disk, you will have very high data rate simply because of the linear velocity being larger. Okay, and some one question may be, hey, why don't I slow down the disk when I'm trying to read at the periphery so as to keep the data rate the same, right? First of all, that's an impractical idea, because slowing down a disk which is spinning, right, is likely to take a mechanical time constants are several orders of magnitude slower than, or smaller in time constants are much larger than electrical time constants. So physically slowing down a disk is impossible, and you know that data is not all written in the same physically contiguous locations, right. Files are split up often, and then some of it is written here and then some of it is written there. So during a file read, you may have to read at the outer part of the disk, and then the rest of the file may be written somewhere else on the disk, and so on. And so if you keep slowing down disks and all this, you can go and have tea and come back and you'll still be reading the file. You understand? So since data rate varies by a large factor, 3 to 1 is a big variation. Okay, you not only have to have a filter whose bandwidth is high, the bandwidth also has to be variable by this large factor, 3 to 1, plus you have to add variations due to, you have to also compensate for variations due to process and temperature and all this other stuff. So in principle, you'll need a filter whose bandwidth varies by a factor of 5 or so, okay, to account for both process and temperature variations, as well as simply the need to program the filter bandwidth over a wide range. Okay, so it's in this niche application that GMC filters are used without exception, simply because the linearity required is modest, right, and the speed required is very, very high. All right. So,
What is the bandwidth variation?
pardon?
The bandwidth variation I did not follow. It is due to the change in the 3:1 speed.
Yes.
So the bandwidth.
So see, what is the need for the anti-alias filter here? What is the need for the filter here? It is to eliminate high frequency noise outside the signal bandwidth. Now, if the data rate is reducing, it means that the signal bandwidth is also reducing, which means that you can't have a fixed frequency filter, because if the filter bandwidth is too high, then you are unnecessarily passing a whole bunch of noise which you don't need at all, right. So when the data rate reduces, you reduce the bandwidth of the filter. When the data rate increases, you want to push the bandwidth of the filter out also. Another thing is that you also want to maintain the same characteristics. The shape of the response must remain the same whether you are at the inner diameter or the outer diameter, correct, because everything in the channel remains the same. It's just that time has been stretched, that's all. So the rate at which you sample in the AD converter will reduce at the inner diameter, the filter bandwidth will reduce, right, and so on and so on. Is this clear? So even though we keep saying GMC filters are not great, right, every technique which has one, some merit or the other, right, will always find some niche application, right. So this is one example where probably no other technique will work, simply because of the speeds involved. Okay, all right. So in many other applications, speeds like this are not necessary, right, and a good example being say for example wireless LAN, right. The data rate in wireless LAN, depending on which variant you are using, is several megabits per second, right. So the is either 11 or 54 or something, right. So the bandwidth of the channel, right, the analog bandwidth is about 20 megahertz or so, I think. So, when you translate it down to baseband, it will turn out to be that you will need filters either 10 megahertz or 20 megahertz bandwidth, right. And so, these bandwidths, as you can see, when compared to the bandwidths required for disk drive applications are down by almost, I mean more than an order of magnitude, okay, almost 2 orders of magnitude roughly. So, for all practical purposes, these are considered low frequency filters because the bandwidths are just of the order of several tens of megahertz. There are other wireless standards, for example, WCDMA and all these things need filters with bandwidths of 1 megahertz, 2 megahertz, that kind of thing, right, all baseband stuff. But these applications, especially wireless applications, typically will require filter linearities which are very, very high. The reason why they require filters with high linearity is the following. Let us say you have a filter whose bandwidth is, say, a cutoff frequency is 1 megahertz. So, in other words, you are supposed to select stuff which is within the 0 to 1 megahertz frequency band and reject stuff outside the band. But as we all know, all filters will fundamentally be non-linear, okay, because the integrators use transistors are non-linear. So, it follows that the integrators will be non-linear. It is only a degree, it's only a matter of degree, whether they are very non-linear or less so. Now, if you take a weakly nonlinear system and you put in 2 tones, let us say you have, for argument's sake, I will take a simple nonlinear amplifier. The output, as you have seen in your assignments, can be modeled if the linearity is weak. If x is the input, y can be modeled as some a1x plus a3 x cube plus higher order terms which we neglect, correct. Now, and why have I dropped a2x square? We have said all our signal chains are differential anyway, so even order nonlinearity can be largely neglected, okay. So, now if x is a cos 2 pi f1 t plus a cos 2 pi f2 t, right. What is y? Y is nothing but a1 times a cos 2 pi f1 t plus a1 a times cos 2 pi f2 t plus what? Come on, people. A3 times cos 2 pi f1 t plus a cos 2 pi f2 t the whole cube, and this is nothing but the linear part plus what is this, the expansion of a plus b the whole cube, a cube plus b cube. So, if you cube this term, what all components will you get? Cos 2 pi f1 the whole cube. So, you will get something at something proportional to, I will just remove all the constants of proportionality, I will just say proportional to a3 a cube, right, because a cos 2 pi f1 t whole cube will be A cube, it will also be multiplied by A3, correct. So, A3 A cube at 3 F1 and also a small component at the fundamental at F1, which we can neglect because A3 is supposed to be very small compared to A1, right. Similarly, if there is a the whole expression is symmetric with respect to F1 and F2. So, if there is something at A3 with amplitude A3 A cube at 3 F1, there will also be A3 A cube at 3 F2, correct. Now, what happens to the cross terms? Right. So, 3 times A square cos 2 pi F1 t the whole square times A times cos 2 pi F2 t, correct. The cos square at F1 will give something at DC and 2 F1. So, DC and 2 F1 will have to be multiplied by F2. So, that will give one term at F2 and one, it will give you other terms at 2 F1. So, this will be proportional to again proportional to A3 A cube, some term at 2 F1 minus F2 plus another term at, because of symmetry, 2 F2 minus F, correct. Pardon? Yeah, they will also be correct, plus also terms at A3 A cube 2 F1 plus F2 2 F2 plus F1. Okay, I have not written down the values of all these constants. They will be, you can work them out. That is not important. So, let us kind of picture what there is here. You put in F1 and F2 and sure enough they are there in the output, correct. So, this is F1 and F2. So, what is there are also terms like 2 F1 plus F2, which is where do you think that will be? Way off, right. So, say P4 2 F1 plus right. So, this will be 2 F1 plus F2, okay. 2 F2 plus F1 will be, it will be further off because the difference between the two of them must be 2 times F1 minus F2. F1 F minus F2 is 1 unit on this paper. So, it must be 2 F2 plus F1 must be there, correct. Then what about 2 F1 minus F2? It is F1 plus F1 minus F2, right. So, F1, the magnitude of F1 minus F2 is this character here. So, F1 plus F1 minus F2 will be a term here and another term. Similarly, 2 F2 minus F1 will be that character, correct. So, these products are what are called intermodulation products. All right, and they, as you can see, what all can you observe? The amplitude of these products is proportional to this. Makes intuitive sense. One, it must depend on A3 because if the system was nonlinear, was not nonlinear, this won't come out in the first place. And what is the intuition behind A cube? Yeah, I understand if you increase the signal by a factor of 2, a cube increases by a factor of 8, but what is the intuition behind a cube? Why not a to the power 5? Because the cubic term, right? I mean, cube means what? The signal is getting multiplied by itself and again getting multiplied by itself. So it must follow that the distortion term must be proportional to a cube, correct? So, again, this is only possible if you put in two tones F1 and F2, you can get tones other than F1 and F2 only if the system is nonlinear, right, or time varying, which will not consider here. So, time invariant system can produce tones at frequencies other than the input frequencies only if it is nonlinear. Okay. Now, so if let us say therefore, the input to this filter which we have built is say a 2 megahertz tone here and a 3 megahertz tone here. You understand? If the filter is absolutely linear, what do you think will be the output of the filter? It should be 0. Why? Because 2 and 3 megahertz are in the stop band of the filter, they will get eliminated by the filter. Now what happens? There will also be a component at 1 megahertz, right. So this is the result of intermodulation of these two tones showing up within the signal band. You understand? So this basically is a, I mean, this is obviously a problem because we can, since we didn't know that the filter was nonlinear, where we take everything coming out of the filter as being the desired signal, we now see that tones which are outside the filter bandwidth can cause components within the signal bandwidth because of nonlinearities in the filter. Now this is a particularly a serious problem in RF systems or in wireless systems because of the following. Finally the message that you are trying to send, right, is placed on a channel. There are many such channels which are combined into a band, correct. So if let us say you are trying to receive a weak signal from a base station and you have two of your neighbors also calling at the same time, right, then what happens? Your cell phone is receiving a weak desired signal, right, and two very strong undesired signals, right. Now if the filters inside were not very linear, I mean finally this is all happening at RF, but everything has to be demodulated down to baseband, correct. I hope you all understand what modulation and demodulation is. Okay. So when you demodulate them down to baseband, your desired channel will be at baseband, right. Neighboring channels will be outside, will not be at baseband, and so therefore what, to get rid of those other channels, what you do is put a filter. Now the filter is not linear enough, then your desired signal is very weak, something like this for example, right. Okay, probably wider band than this, right. But now even though your desired signal is weak, okay, the interferers are very small, very large, because they are, your friends are next door, whereas the base station is 3 kilometers away. You understand? So the interferers can be many times larger than the desired signal, and if your filter is not linear enough, what will happen? These two tones will beat through the nonlinearity and appear in band, corrupting your desired signal. Just hold on. Excuse me. All right. So as you can see, nonlinearities in the filter can be a serious problem, right. And please note that in this case the desired signal is very small. So one might think that, hey, anyway the signals which are out of band are going to get eliminated, so why should I bother about linearity in the filter, right. But thanks to these terms, right, A3 times A cube, where A stands for the amplitude of the interferer, right. So, A3 times A cube can be very large, right, even though the desired signal is very small. This can cause corruption of the desired signal and therefore, dropping of calls and so on. So, it is very important that the filters that you use have adequate linearity, right. Now, speed is no longer issue because the bandwidths of these systems are somewhat small. Okay. Now, the question is, what do we do about, I mean, how do we go about realizing these filters? Should we go and burn more and more power in the GMC filters and make them linear, or is there a smarter way of doing things, right? Given that the key advantage of the GMC, which is speed, is no longer required, it is likely that we can play some circuit tricks, right, which would take some time. I mean, to play tricks you need some time, right. That time you just cannot afford in a GMC filter because the frequency is at which you need to filter very high. Okay. Perhaps now, because there is so much time, we can indulge in a little bit of more exotic circuitry, so as to achieve linearity, right, and the bandwidth that the circuit needs, the time that is needed to do all this may not be very large, or even especially considering the fact that the filter bandwidths required are very small. Is this clear? So, what is the best workhorse in order to if you want to linearize something, right? So, as we have seen in our discussions on negative feedback is a nice way in which the linearity is governed only by the feedback network, right, which can be very linear because the feedback network can be made with passives, correct, which are fundamentally a lot more linear, at least in principle infinitely linear when compared to transistors or active elements. And the good thing about negative feedback is that as the gain, as the loop gain keeps increasing, we find that as the loop gain tends to infinity, rather the closed loop gain simply becomes 1 by the feedback path gain, right. So, if you use a linear feedback network and attempt to get as high a loop gain as possible, then we should be in principle able to achieve linearity without having to bother too much about the linearity of the active elements themselves, right, because negative feedback is actually taking care of all this. Does it make sense? Okay. Now, how would we linearize and so getting back to how one would attempt to realize an integrator. I mean, the basic building block we have seen so far is the integrator, right. The GMC, I mean, the GMC came about by thinking about a way of converting. I mean, we said that inductors and capacitors which are needed to make filters are integrators. The only problem is that the domains, the input and output domains are different. In a capacitor, the input is voltage, current, the output is voltage. In inductor, the input is a voltage and the output is a current, where the output is expressed as an integral of the input. Now, if both the domains, input and output domains were the same, then we could combine these building blocks, put them together and get arbitrary transfer functions, right. One way of doing that was to convert the input voltage into a current, correct, integrate the current onto a capacitor and get an output voltage which is an integral of the input voltage, that is the GMC integrator, right. And then once you have this building block, you put many together in all sorts of topologies and get whatever transfer function you want. So, the question now is can we do that with, can we achieve integration with op amps, right, where negative feedback is used to realize very high linearity for the integration process, correct. So, in other words, can we for example use the basic idea is to convert an input voltage into a current and push that current onto a capacitor, right, and look at the capacitor voltage, right. So, in other words, what we need to do is to convert the voltage, input voltage into a current, pass this current through a capacitor. Capacitor voltage is the desired output, right, but we want to use negative feedback to convert. So, what kind of controlled source is this? Okay, all right. So, if let us take, what kind of control source is this part? A current controlled voltage source. So, how will you realize this? Using feedback principles. If I have a current, right, and I want to generate a voltage which is Z times this current, how will I want V out which is Z times I in. Okay. So, what we can do is pass this current through some impedance Z. Okay. So, if you are in the lab for example, you would put a voltage here, correct, and what would this voltage be? I mean, let us say you are in a lab and you had a variable voltage source and you wanted to make V equal to Z times I in, correct. So, what will you do? You compare V minus I in Z. So, V minus I in Z is nothing. How will you realize I in Z? You pass I in through Z. So, this drop will be I in times Z. This is V. So, this voltage will be V minus I in Z. So, this must be compared to ground, and if this voltage is too small, what happens? If this voltage is smaller than ground, what does it mean? V is too small. So, I must increase V. So, if this is small, this must go up. So, what must be the signs in the op amp? Yes, minus on the left side. Very good. Okay. So, if I draw this in another way, okay. So, what is the potential at this node if the op amp is ideal? 0, correct. If this potential is 0, what must be I mean, then one can say, hey, this potential is 0, so do I need really a current source after all? In other words, do I need an ideal current source? Even if the current source is non-ideal, for example, let us say this was R, what is the effect of R? There is no effect, right. I can use a non-ideal current source. In fact, I can use a very bad current source and still I will be okay if the op amp is ideal. So, I can always replace this I in times R by a voltage V in R okay. So what happens to the output voltage? V in by R. What is this current? V in by R, okay. So what is this current? V in by R. So what is output voltage? Please look carefully, people. What is the output voltage? No, no, okay. Minus V in by R times Z. You understand? It's important to note this is an inverting configuration. Okay. So instead of Z, if I put if Z was a resistor, you get the well known inverting amplifier of gain 1. If this is a capacitor, this will be minus V in by SCR. Okay. Now the same thing can be done for a fully differential op amp. Okay. In which case okay. Now if the difference, if this was VCM plus VI and this is VCM minus VI, then all that the op amp is enforcing is that through negative feedback eventually the difference between these two nodes is 0. It does not say anything about the absolute value of these two nodes. Okay. So which means that the differential current flowing like this, right, will be Vi by R, this will be Vi by R, with output common mode voltage is forced to VCM using a common mode feedback loop, okay, as usual. This voltage must be VCM plus Vi by R times SC, sorry, VCM minus Vi by SCR, this is VCM plus Vi by SCR, correct. And in a fully differential system, getting an inverting or non-inverting integrator is trivial, because it is just flipping the wires. Okay, this is the differential equivalent of the single-ended integrator structure. Yes. No, it's coming from some other signal, right? Some differential source is driving it. That will have a, should have a well defined common mode. Yes. This is coming from two voltage sources, isn't it? It must have a well defined common mode. Yes, the input common mode of the op amp is what now, tell me? The question is, what is the input common mode voltage here? Why should it be VCM? At DC, no current flows to the capacitors, correct? Which means that these two voltages, the common mode voltage here must be the same as the input voltage. Is this clear? Yes. Okay. In practice, I mean, see, one thing that you should all know by this time is that no integrator will ever be operated open loop, because even a small DC input, right, which will obviously happen because of mismatches inside and so on, will cause the integrators to saturate. So, for those of you who have done the undergrad lab, you would have found that when you built your, if you take just a 741 op amp and even you short its 2 inputs, you would expect that the output should be 0, but it will not, it will either be plus VCC or minus VEE, and that is because small offset will cause the op amp to saturate. So, all these pictures which assume automatically that these are virtual ground, implicitly the assumption is that there is overall negative feedback. These integrators are never operating open loop. Does it make sense? Okay. Now, so in order to prevent the pain of drawing, this structure, people will continue to draw single-ended structures where the understanding is that we can always make a single-ended structure differential at any time without any problem at all, right? Okay. So, if the op amp is ideal, then this is the single-ended equivalent of the integrator, and since we are going to be eventually only designing differential circuits, you will often find -1 being put everywhere you need an inversion. You understand? So, given that we are familiar with GMC integrators and how to build a biquad using a GMC integrator, one has to be positive GM, one has to be negative GM. This is C1, this is C2, right, and there is in principle a resistor, and then a transconductor which converts input to a current. This is topologically a GMC biquad. What kind of output is this? This is the band pass output, this is the low pass output, and as you can see there are 2 integrators in cascade. This integrator is an ideal integrator, GM by SC1. What kind of integrator is this? This is a damped integrator. Okay. So, if you want to draw an active equivalent of an active RC equivalent, please note here that this consists of active elements, the op amp R and C. So, this is called an active RC integrator, right, and the unity gain frequency of the integrator is 1 by RC and is determined by passives. Okay. Now, if I want to realize this character, okay, how will I realize this using active RC form? So, this voltage VLP is the integral of VBP with a negative sign. So, if this is VBP, this must be VLP. Okay. Now, what is VBP? It is a damped inverted, it is a damped integrator with a positive sign, correct. So, you must take this, pass it through a damped integrator, right, and then invert. Okay. So, how will I get a damped integrator? Yeah. So, a damped integrator is one where you make the capacitor lossy. So, okay. All right. So, this is the damped integrator. Is this inverting or non-inverting? It is inverting, but what do you want? Non-inverting. So what should I do? I put a -1 with the understanding that in fully differential form it's trivial. Okay, and this must go to, this must be the VBP. Okay, you understand? And what is happening here? How is the input being pumped? The input is pumped as a current into this C2 R combination. So what should I do here? The input must be converted into a current and pass through this impedance, right? So where should I inject the current? At okay, so the idea is you need to add an input. You need correct. So this is the input current, correct. So that can be, this voltage is anyway virtual ground, correct. So I can you understand, okay, because this is no, the input is getting converted into a current and injected into the RC, correct. And the voltage across the RC is the band pass node. Similarly, here the input is getting converted into a current through R and pushed into the RC parallel combination, correct. The voltage across the RC parallel combination, which is this voltage, is the VBP, inverted version of the band pass voltage. Does it make sense? This is simply a direct correspondence between this diagram and that diagram. Okay, so now if I draw this in textbook form, okay, and if you had only single ended op amps, how will you realize the -1? Use an inverting amplifier with gain -1, right. This is what you have done in the lab. You understand? Okay. So we will continue with this in the next class.